Welcome to today's webinar. Today we show you how to carry out the nonlinear analysis of a plate girder with RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the German and English webinars, technical content of the website, customer projects, newsletters, and so on. I will be the moderator today and I will answer your questions during the webinar. My colleague, Dr. Jonas Bien, will be the presenter today. He's responsible for customer support and for the product development of the steel add-ons. I show you now how you can ask questions, at least for the attendees who participate the first time. At first, I switch off my webcam that you can see the full screen. If you have a question, just press the button with the question mark, then enter your question in that field, press send, and I will receive your question and I will answer you. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, that's at the moment all from my side. I hand over to Jonas. Jonas, it's your turn.
Yeah, hello everyone. A warm welcome also from my side. Thank you very much for your introduction, Andreas. Today I would like to discuss with you the design of a plate girder in RFEM 6 using nonlinear analysis. Almost 1.5 years ago, I have already shown the basics of a nonlinear or GMNEA analysis within a webinar I held together with Andreas on buckling analysis in RFEM 6. Therefore, I will rather hold back today with regards to the theoretical backgrounds and references. Instead, I would this time rather like to devote a little more time to smart modeling, so how you can efficiently model such a problem here, and the definition of imperfections, which are crucial for such kind of analysis. However, I will have to refer back to at least 2 slides from my old webinar at the beginning to give some basic context. So, first of all, I would like to reiterate the key points of a GMNEA. This type of analysis is characterized by an assumption of nonlinear deformations, usually taking into account large deformations and large rotations, which are generally described as third order theory, and also this is the option that you find for this in our software. Then we also have to consider nonlinear material behavior and an imperfect geometry. The aim of a GMNEA is to consider all relevant influences on the load-bearing behavior explicitly in the model and to reproduce its behavior as realistically as possible. This is particularly advantageous when simple verification checks do not exist for a specific task or deliver highly conservative results. However, in addition to a powerful software, a lot of time should be scheduled for modeling, simulation, and result assessment especially. Also, a certain level of experience in FEM and also some basic understandings of the engineering problem that is going to be solved is strongly recommended and needed for this task. To be honest, we could also design a standard plate girder that we tackle in our example today using formulas given in Eurocode 3 Part 1.1 and Part 1.5. However, if we want to examine special design variants of such standard girder, e.g. the influence of web openings in critical regions, or we want to investigate how the plate girder performs when we use corrugated webs instead of plain ones, or we have discontinuous sections. In these cases, a GMNEA can often be the most economical design method. In addition, the GMNEA provides a good insight into the actual load-bearing behavior of components, and in the case of these plate girders, it is very interesting to study the interaction of global and local instability phenomena in one member. Some rules for the application of a finite element method in this context are given in the Eurocode 3 Part 1.5 Annex C, and this will be shortly replaced or will be in short replaced by a dedicated Eurocode that's dealing with finite element methods and its application for steel structures, and that will be bundled in the Eurocode 3.1.14 in the second generation of the Eurocode. And I will refer to this new code as well during this presentation. You can think of the GMNEA as a virtual capacity test, which means that the design load is increased by a load factor until a clear state of failure is reached. Two limit states are defined in Eurocode 3 Part 1.5 for the definition of failure and the determination of the critical load factor, which is the minimum of the following. The load factor when the maximum of the load deformation curve is reached, as shown here on the left side of the slide, and the load factor when a maximum value of the principal plastic membrane strain is reached. This is usually given by the annex or the base code as 5%, which is tolerable, but there might be some additional requirements in the national annexes. The critical load factor is then the minimum of those two alpha U values, and this is then checked against the product of two safety factors on the resistance side, namely alpha 1, which describes the uncertainty of the numerical model, and alpha 2, which describes the uncertainty of the load and resistance model. Here it is recommended to stick to gamma M1 if the observed failure mode corresponds to stability, or gamma M2 if we see that the maximum plastic membrane strain is reached. So let's move on to the description of the design example for this webinar. We have a welded plate girder with a total length of 18 meters, simply supported at its ends. There are some virtual purlins that are not explicitly modeled that rest on top of the top flange at the ends and also in the quarter points, transferring loads from the roof structure maybe to the plated girder and also at the same time supporting it laterally. To avoid local instabilities at those load introduction points, we place stiffeners below them, and we should also take care that the end posts or the end stiffeners are detailed as rigid end posts, so they can anchor back the membrane forces and avoid excessive deformations of the external shear panels. The cross-section is shown here on the left side, so we have a very slender web plate with a height of 1 meter and a thickness of only 5 millimeters. And the flanges have dimensions of 20 millimeter thickness and a width of 360 millimeters. The material is a mild steel S235. All right, after we clarified this, let's go into the program and start modeling this. So I have already prepared a fresh file where we can now introduce the plate girder. As you can see, I have no objects here whatsoever, and also if we look into the base data of this file, there are no specific options activated. It's all a standard type of model, 3D and so on. Okay. So first of all, let's start with the material. We said we want to use an S235. So let's choose one. I always like to choose one that is related to Eurocode 3, but another one would also work. Then let's move on with the modeling of the member itself. We could either directly go with the surface definition and try to place the flanges and the web plates in the correct locations, and also then we have to assign the correct thicknesses and so on. But we can also use another way. We can first start with a member that has the correct cross-section, and then we transfer this member into a surface model. So I start with defining a parametric welded double symmetric eye section in my section dialog with the respective dimensions that I want to have. So height is 1020 millimeters, width 360, width of the flanges of the web would be 5 millimeters, and the flanges 20. So now it more or less looks like the picture that I have shown on my slides. I accept via OK, and then I just place 1/2 of my plate girder in the model. So one span was 4.5 meters, so I want to take in the initial model 2 panels, and then we can later mirror it. So before I generate surfaces from this member, I also divide it, because I want to have a stiffener and some load introduction lines at the central position here. So I first divide this member with one intermediate node, and then I move on and generate surfaces. And what this does, it already automatically generates these thicknesses that I need to represent this section in a surface model. It creates the nodes, the lines, and finally the surfaces that are necessary for this model. So this is a good starting point, I think. Next, we want to create the stiffeners to finish the surface modeling part. Therefore, I need an additional thickness of 12 millimeters that I wanted to use for the stiffeners. I can also write a reminder for myself that this is for the stiffener, this is the web plate, and this thickness is defined for the flange plates. Okay, I agree. And then I just place some rectangular surfaces in those positions where I later want to apply the loads. And then if we think about this as being the left part, the left half of our plate girder, we also said we want rigid end posts. So I would generate this by adding some outstanding cantilever part here with an additional stiffener to really have a very compact section at the end that can serve as a rigid end post. And I can come to this modeling variant by just copying, for example, this panel here to the end. And then we know that the length of this is also 4.5 meter, and I want to have a very short and compact cell here at the end. So I just move the end section here back towards the end of the initial position of this stiffener here by, let's say, 4.2 meter. And then I have a nice rigid end post here without needing to define additional surfaces by hand. Okay, so, oops, didn't mean to do that. All right, so then we can check maybe if we assigned the correct thicknesses. I always like to check the rendering based on the thickness. So we get a nice overview of what thicknesses are represented in the model and where they are. So this seems all fine to me. So we can continue with assigning the supports. And I want to avoid singularities at the vertical supports. So I try to use line supports at this second line of the stiffener here. And I just want to support this line in Z direction. I don't want to restrain any deformation along the line or in transverse direction. So I only support, I already see another problem because we defined those rectangular stiffeners here over the existing section or the existing surfaces. We have some double lines here, and we can quickly merge them by just cutting and merging them via this tool. And now we have single lines here in these locations. So that's a quick fix. And now I move on and assign the vertical supports here at these two lines. Then I need to take care of the lateral supports these I assign as nodal supports in some points that are very stiff. So first of all, I have my lateral supports that I wanted to assign in at the ends and also in these quarter points. So I choose as a point of reference the crossing between flange and web plates and the stiffeners. And then I also need to make sure to also couple this point here in Y direction so it does not tilt. And also I need to somehow support my model in X direction. And that's why I also want to define one support in global X and Y direction at the lower flange here, like here. All right. So that would also be the respective supports conditions that I want for my half model. I can later just also mirror them when I want to create the full model. But before we do so, it would be wise to also define the loads, because there we can also leverage on the mirror operation. So we go ahead and define our loads. Maybe one look back to the task description. Yeah, here we can already see that we have concentrated loads, 3 different loads here in the endpoints or above the endpoints and the quarter points. The first one represents dead weight. The second one comes from snow, and the third one comes from wind pressure. So these I want to define separately for those 3 load cases. So let's start with the definition of the, or maybe we start with the definition of the dead load here in the first case. So let's do that. I want to apply those loads as line loads, also again to avoid singularities when using nodal loads. And I could now go along or start with calculating my equivalent line load for a concentrated load of, for example, 15 kilonewtons by hand. But I could also use load distribution type uniform total, where the program does this job for me. And I just have to enter the total load that I want to apply over the length of one line. And since I have 2 lines here, I need to divide my 15 kilonewtons by 2 to get the total load for one line. I want to apply this in Z direction, and now I just need to select those 2, assign this, and RFEM already calculated the correct kilonewton per meter value for us. If we multiply this value by 0.36 for the width of this flange, then we get 15 kilonewtons in total as we wanted. Okay, we can then just copy this definition to the internal lines or purlins where the load is transferred to our plate girder. Here we had a slightly higher load of, I think it was in total 25. So each line gets 12.5 kilonewton. And this definition we can also copy to the central lines here. And now we make a smart move and generate our second and third load case from our first load case. And we do this by copying our first load case. This means that also all loads that we defined in this load case are copied. So we just have to change the action category. Now in the first place, I want to define the snow loads, and we have to take care to deactivate the self-weight if we copy from the self-weight load case. Otherwise, that would be considered twice. And we do the same for wind. Choose the appropriate action category and click OK. And now we can go to the table. This is the easiest way I find to manipulate those load values, because we just want to change values. As you could see here in the slide, we have the same load type for all load cases, just different amplitudes. So for snow, we would have 20 kilonewtons and 40 in the external positions, and for wind it would be 2.75 and 5.5 in the internal positions. So we just need to change the values basically. So let's do this via table. For the snow load, we had 20 kilonewtons divided by 2 and 40 kilonewtons divided by 2 in the internal positions, and then for wind it was 2.75 divided by 2 and 5.5 divided by 2. This gives us the respective concentrated load distributed to those lines. All right, and I think then we can already mirror the whole thing. Maybe I don't want to mirror this load here, because we have already defined this for the central position. I don't want to do that again. And now I mirror all the selected objects about the YZ plane, and the plane should go through this point here. I make sure to copy the included loading and click OK. And now I think by doing so, a copy included loading, it also recognized all the loading on these lines and copied it, although I did not manually select it. So now, as you can see, we have a double load here, and we just quickly delete this. Okay. Then I only need to do one additional modification of this mirrored part. I don't want to hold the plate girder in X direction on both sides. I don't want to activate any membrane forces here coming from large deformation in X direction. So I, instead of using support in X and Y direction here at the end node, I just copy the definition from above and just place a nodal support that supports in Y direction here instead. So it is free to move in X direction now. Okay. Then one more important part when creating a surface model in the context of steel design. Usually our base settings for the mesh are not really suitable. This is element length of 0.5 meter are more suitable for, I don't know, concrete slabs and foundations. So not for us. Otherwise, we would only have 1 or 2 elements over the height of our plate girder, and that wouldn't be sufficient to get a good model here. So we just use 5 centimeter in the first step and check the mesh visually to check if it is reasonable. And I think in the first step, this is all fine. It is always advisable anyway to, in the context of a GMNEA, to make some sensitivity study of the mesh refinement at some point. But I think this is a good starting point here, this level of refinement. We can also check if we defined the model properly by just running one test load case, for example, load case 1, and see if everything is connected properly, if we have supported the model sufficiently. And it looks quite okay to me. The deformation shape looks as expected. As I said, it can deform in X direction here at the end, so no restraining forces in actual direction. We can also check the stresses in X direction. We have only bending here, so everything as it should be, and this is fine. Then maybe we need to think of a combination of our load cases. So let's go there as well. By default, we have 4 different design situations that RFEM generates for us in a new model. We only want to do checks in the ULS combination. We only want to check our model for strength. So we leave that in, and that gives us, with the combination wizard activated by default, 5 different load combinations. But for us here, it is very easy to see that load case or load combination, number 3 results in the largest loading, or is the most critical loading combination for our case here. So because I know that GMNEAs are quite heavy on the computational time, I want to reduce the load combinations I need to take into account to a minimum. So I deactivate the combination wizard, say I want to keep all the load cases, load combinations, and then I manually delete all other load combinations and only leave CO3 for later analysis. And then in the first place, or in the first step, I use first order theory for analysis. Okay, I think that's it for the definition of our base model, and we can now tackle the special ingredients of the GMNEA. So let's start with the imperfections. According to Eurocode, residual stresses resulting from the manufacturing process of steel girders need to be taken into account. These residual stresses originate from uneven heating and cooling of the material during manufacturing. In a plate girder, very high local temperatures and corresponding material expansion occurs when the web and the flange plates are joined by welding. The individual cross-section parts are joined in this heated state. And if the component then cools down again, constraint-free contraction of the material is no longer possible, and residual stresses remain in the cross-section. Those stresses are in equilibrium with each other across the cross-section. The stresses shown here on the lower right side are specified in the draft version of Eurocode 3, Part 114 for welded double symmetrical I sections. In principle, it is possible to consider such residual stresses in RFEM, although a bit cumbersome. But since we occasionally receive customer requests about this, I would like to show you in a short excursus how to approach this problem. Maybe before we go into the software, I would like to give you some hints or explain some basics. So in RFEM, we cannot directly define a residual stress state, but we can use a residual strain state, or we can apply an internal strain state. And since we know that in the elastic state, stresses and strains are coupled by Hooke's law. So if we look into a stress-strain curve in the linear elastic regime, at least, stresses and strains are proportional, and the proportionality is given by the Young's modulus. So for the stress we are looking for is defined by the strain times E. And since we know the stress that we need to apply, it is given in the Eurocode, like we need in the tension sections stress as high as the yield strength. And then in the compression parts, fourth of this, we can compute back the required axial strain that we need to define in RFEM. Then secondly, in RFEM, we can only define a constant strain state or a linear strain state. But we have some progress of this curve over the flange that cannot be described by one of those definitions. So we have to divide our flange plates into parts that are suitable for this actual strain definition. So for example, we can divide the flange plate here and there. I try to draw this as accurate as possible. So we have one constant block here, one constant block here, and in between one linear part. And that's exactly what I have already done in a separate file. So that I want to show you now. So let's switch to RFEM and open the respective file that I've already prepared. In this case, in the German webinar 2 days ago, I modeled this from scratch. So when you are interested in how to model this thing, basically I copied a part of the plate girder model, divided my surfaces on these intermediate points that I just indicated in the PowerPoint slide, to be able to add these strain definitions here. But it took so long that I don't want to stress my time limit again today. So if you're interested in the modeling procedure, you know now the background, then head over to the German webinar and see how I've done it. But I want to explain the most important steps here. So I've divided my model basically, and then I applied an actual strain state. You can find those under surface loads, load type actual strain, and there you have you can choose between a uniform and a linear load distribution. And in this case, for this constant strain or stress block, I defined only a uniform distribution with a magnitude of 0.3. And if we check, I've entered this via formula. So I just divided my yield strength by the Young's modulus and divided it by 4. This leaves us with a positive strain, and the positive initial strain leads to later compressive residual stresses. We will see that when we run the simulation. Similarly, I did the same in the middle of the flange plate, where I just defined a block of actual strains with a negative sign now, and this is just described by yield strength divided by Young's modulus. And then in between, I applied this linear load distribution. I used 3 corner nodes to describe the distribution of my loads. You can check also this out in the German webinar if you're interested, but it's pretty straightforward. And here I just defined 2 nodes with a tensile strain and one with a compressive strain to get this distribution over the flange plate. And I did the same basically for the web plate as well. So what I've done also was I changed the mesh size a bit. So I chose very small element edge sizes. So I have at least 2 elements over each surface. So we can also see this linear or this gradient in the stress distribution here. So we can actually represent this with the mesh size. Yeah, and that's basically it. So let's check the results. I have already computed it. Maybe one last note. On this end of the girder, I have applied some line support, where I just like held basically every node in place, also in X direction. And this is very important because by doing so on this end of this girder, I restrained every warping of the section and every deformation in X direction, in longitudinal direction. On the other end, I didn't do that. So here all my filaments or fibers of the section are free to move in X direction. And we can see that this has a great influence on the resulting stress state. So here where we have more or less a disturbed state, so where movement is free in X direction, basically, you can see that those residual stresses actually vanish, and they diminish here at this free edge. But basically, this is what happens in reality as well. If you have such girder and you would cut it in some plane, then these residual stresses would be freed, and you actually see that on the deformation shape. So the section would go into the wanted shape, or into the shape it wants to go after with the residual stress state, and that would be the way it would look at this free edge. Of course, this is exaggerated here, so the resulting deformations would be very small, but that would basically happen in reality as well. On the other edge, I held every node in place, so it cannot happen there, just to show you the difference and the behavior that we get by simulating this effect. Let's check the stresses again. So I've now here shown the stresses in X direction, and we can already see that we have compressive stresses in these blue areas, and in the red areas we have some tensile stresses. It's not very good to see the actual numbers. That's why I also inserted a section here in the middle with a certain distance to the member ends to have an undisturbed region. And maybe we can also check the stress state in this section. And here we actually see that in these tensile zones between flange and web plates, we have almost exactly the yield stress as a residual strain, and in these compressive parts, we have Fy divided by 4. So this is exactly what we wanted to simulate when we look back into our PowerPoint slide here. So this is one method to apply such residual stresses in a surface model of such kind. Another way would be to not use this load type axial strain, but to define a similar thing via temperature increase. So with we could also apply some temperature, and then with the material properties, we would get we could simulate a similar elongation that the steel would like to make, and since it is restrained over the cross section, we would get a similar residual stress, just that we would need to add an additional step and take into account this alpha elongation factor or expansion factor of the steel, which makes it a bit more complicated. So this is the easy way to do it. All right, but this was just a small excursus. Let's get back to our actual model. Of course, I will also upload this smaller residual stress model with the slides, so you can study this for yourself. Okay, back to the presentation. We have now talked about one relevant type of imperfections, which is the residual stress, which comes from the manufacturing process, as already explained. In addition to the residual stresses, we also have to take into consideration geometric imperfections. These simulate deviations from the standard dimensions or misalignments of elements during erection on the construction site. We know such geometric imperfections from Eurocode 311, for example, as well. And this is exactly what is meant with this type of geometric imperfections. So we could either specify residual stresses and geometric imperfections separately, but we have seen how cumbersome already the definition of the residual stresses can be. And also for some section, we might not even have a clear statement for how to approach this residual stress problem. For a double symmetric welded eye section, we have this the definition given in the Eurocode 3 part 114, but there may be cases where this is not applicable. So luckily we have some alternative, and the Eurocode 3 part 1.5 also allows us to take into account the residual stresses not explicitly, as we just did it in this small model, but by increasing the base geometric imperfections. So just apply geometric imperfections, just take those into account and increase it by some factor. Both types of imperfections are then summarized as equivalent geometric imperfections. And this is the approach that we want to take for our plate girder actually. So let's look into those equivalent geometric imperfections in more detail. And the good thing is that we actually don't need to increase the geometric imperfections by ourselves, but the magnitude for those geometric imperfections is actually given in the Eurocode 3 part 1.5. And these already contain the residual stresses. So Eurocode 3.1.5 describes 4 different types of geometric imperfections that we need to take into account if applicable for our problem. The imperfection for longitudinal stiffeners, shown here on the bottom, is not relevant for us since we don't have any longitudinal stiffeners in our example. However, global member imperfections, as shown above, or which would be the first type of imperfection shown here, need to be considered. And we are familiar with this type of imperfection from Eurocode 3 part 1.1, as I said already. And this exactly what is referenced here in Eurocode 3 part 1.5 for the imperfection amplitude of this geometric equivalent imperfection. So we would go in Eurocode 3.1.1 to check what or how large our imperfection amplitude would need to be. But before we do so, of course, we need to think about what type of bow imperfections are relevant for our case here. Since our girder is loaded in bending about the major axis only, so we need only to consider imperfections for lateral torsional buckling. And according to Eurocode 3 part 1.1, such imperfections should be affine to the imperfection for flexural buckling about the weak axis, but with half the amplitude. So to find the specific amplitude, we go to Eurocode 3 part 1.1, check table 6.2 to see what buckling curve we actually have for buckling about the weak axis. And in our case, we would find that we have a welded eye section with a flange thickness less than 40 millimeters, and we would choose buckling curve C. Next, we would check table 5.1 of Eurocode 3 part 1.1, and we would then choose the imperfection value for a plastic section check. In the end, we are doing a nonlinear analysis with nonlinear materials, so we are also accounting for redistribution in the cross-section, which means we basically want to do a plastic section check. And with this information and with the information of our buckling curve, we can then read the imperfection amplitude for our equivalent imperfection to 1 divided by 150 for buckling about the weak axis. And we would then need to take half of this for our lateral torsional buckling imperfection. The last question is then to which length does this value refer? Our flange is under compression and held in the quarter points, so we apply the imperfection alternating between those intermediate supports, as also shown above in the figure here on the slide. So let's just apply what we have learned to our actual model. In RFEM, we have several options to define geometric imperfections on surface models. And for the first type of imperfection, this bow imperfection along the member length, the most suitable one would be to apply a imperfection affine to the static deformation shape. So let's do that. And it will get clear how the concept behind this is during modeling, I think. So first of all, we define an additional load case where we apply a load that gives us a deformation shape of the structure, which is more or less equivalent to the imperfection shape that we want to apply. So first I start with defining a new load case. I name it bow imperfection, static, maybe to remind myself. Action category, for such kind of load cases I get none, because that way I avoid that it accidentally gets combined with other things if I have a load combination assistant activated. And now in this load case I define some loads that give me the deformation shape that I want to take as an imperfection shape. So I would just scale this to a default value. It doesn't matter in the first step how large this deformation appears in the static analysis step. We can scale it later in the imperfection when we apply the imperfection case. So first of all, I want to deform my girder in y direction by defining loads on those lines between web and flange plates. So I avoid that my section itself deforms. I want more or less a member deformation without distortion of the cross section. So I just apply this let's say dummy load in one direction, and then I alternate the direction of the deformation. And now if I run this analysis for load case 4 that I have just defined, we hopefully see some kind of bow-shaped deformation here. Let's actually check the global deformation, and yes, this looks exactly as expected. I get a bow-shaped imperfection, or a bow-shaped deformation shape with 0 points in the inflection points, and the quarter points where I wanted to have them. So this is a good basis for my imperfection shape. You can also see that the deformation here is now the maximum deformation 0.0 millimeter. This is of course a bit too small for the imperfection that I need. We said we want to define the length between these inflection points divided by 300, and that would be 4.5 meters divided by 300, so 15 millimeters. But that can actually be set then in the second step, where we define the imperfection itself. In this case, we want to use an imperfection type static deformation. There we have to reference a load case or a load combination that where we want to adopt the static deformation from, and then we need to scale it somehow. So in this case, I want to source my deformation from load case 4, and I want to scale it spatially, so just as it appears in here when I check the total deformation plot. And I want to set the magnitude, I can just handle it via formula, to 4.5 divided by 300, which gives me 15 millimeters. And now I have this imperfection case 1 here, and this one I can also calculate or simulate, and it will now scale the deformation shape from load case 4 to the value that I want, to 15 millimeters, and that's exactly what we get here. It's nice to check this, and then we can apply this imperfection like as we usually do. Here to, for example, to load cases or to load combinations here with this option. But we are not finished yet. We need some other imperfections that we need to apply to our structure. So let's go back to our presentation. So first step is done. We have the global bow imperfection considered, but there are 2 more geometric imperfections in Eurocode 3 part 1.5 that need to be taken into account if applicable to the problem. And those are the local buckling shape deformations in the buckling panels or in potential buckling panels. And if we use geometric equivalent imperfections, the amplitude of such imperfections should be the minimum dimension of the panel divided by 200. So let's see how we can apply this buckling shape affine imperfection with this specific amplitude in RFEM again. So to get a buckling shape deformation, we of course first need to do a linear buckling analysis. For this, I need to activate my structure stability add-on, and then I get access to linear bifurcation analysis, and I want to set this one up for load combination 3, where my design loads are defined and combined. So for this load combination, I want to get some eigenshapes, and I want to choose the critical from that. So 4 eigenshapes are maybe a bit low number. I want to have some additional information, so I just set this value up to 20. So it will now, after defining the stress state in my structure, calculate the linear bifurcation factors, assuming everything is perfectly linear. So my whole problem is linear, and it will also, besides the linear bifurcation factors, I will also receive my respective mode shapes. So this takes a bit. I want 20 mode shapes, and these are quite a few elements, but it should finish very soon. So now, in addition to the static analysis results, I also get stability analysis results. If you are interested more in this linear bifurcation analysis and what we can do with it, check out my last webinar on this topic. I think it was called something with linear bifurcation or buckling analysis in RFEM 6 and RStab 9. So there you can get a lot of background information and additional info. So what we basically get now are 20 bifurcation factors with the respective mode shapes. And now the question is, of course, which mode shape do I need to take into consideration for my nonlinear analysis? And we can already see that the first 12 mode shapes only affect the external or the outer buckling panels here, while the 13th now we can see first modal deformation in the internal buckling panels. And the Eurocode offers not really huge help here in this respect. It just says that the most critical imperfection needs to be taken into account. This is often not quite straightforward to get. So if we are in doubt, we would need to take into consideration different mode shapes and also maybe different imperfection directions. But for now, or for the start, it is always a good bet to just go with the first mode that actually has the lowest critical load factor in the structure. So we will now, for the first shot, so to say, go with this first imperfection here. And how do we get this buckling shape, or how do we bake this into an imperfection? We again define a new imperfection case, this time of the type buckling mode. This is now available since we have activated the structure stability add-on. It wasn't before, so maybe let's also give those imperfection names. Local imperfection, and okay, I need to finish the definition. So again, as in the static imperfection case, we need to source the deformation from somewhere. In this case, we source it from the load combination 3. And we said for the start, we just take buckling mode number 1. And we also take an arbitrary deformation direction. We scale it spatially again, and as an imperfection magnitude, we set the minimum of the panel dimensions. So panel dimensions would be 4.5 by 1 meter divided by 200. It's always very convenient to just use the formulas to plug this in, and you don't need your calculator. You have a reminder if you are unsure, you can check the formula again and so on. So this is very handy. Okay, so that would be this definition. Then let's also rename imperfection case 1 global imperfection, so we can have a quick distinction between those. And now if we also solve this second imperfection case, we should get the eigenshape that we just saw now, but now scaled to 5 millimeters maximum deformation. So that's perfect. All right, so 2 imperfections are now already defined. Let's go back to the presentation, because there is a third and last type of imperfection that we must take into account, and this is flange twisting to generate. So, and this flange twisting, we need to consider between different sections. So in our case, we have some transverse stiffeners, and between those stiffeners, we need to account for this bow twist, and the bow twist should have an amplitude of 1 divided by 50 times half the flange width. And the question is again, how do we do this in our program? Because neither the static nor the buckling imperfection type are really helpful in this case. But what we can always do in this kind of analysis, we can always like burn or engrave the imperfection into our basic geometry. And I want to show you this as a third option. So this means, of course, we need to redefine the model itself. So, but also in this case, or with the right strategy, that is always that's also not a lot of additional work. In our case, we can just change the type of this line from polyline to arc. Then we set a control point in the middle of this length of this arc, and then we set the arc segment height to the imperfection amplitude. So basically, we need to change this z that coordinate of our control point. I again do this via formula, and I add to it the flange width divided by 2 divided by 50, and apply this change. And now we will see that when we look from the side, this is not a straight line anymore, but it's like curved, and this will lead to a twisted flange in the end. So that's perfect for our imperfection. But we also see that now we have some problem, because our surface here is gone, and we also see that this respective surface is now marked with a red color here. That is always bad, but it's very easy fix in this case, because we defined initially this surface as a plane surface. This is no longer true, because one of the boundary lines is now an arc, and we can just fix it by changing the geometry type of the surface from plane to quadrangle, and this resolves the issue. And now the question is, how do we proceed from here, because there are many surfaces that we need to change. But instead of doing all of this manually, we can again be a bit more clever and delete or use some modification functions to copy this imperfect geometry to the other locations along our member. So in the first step, we could mirror this surface over the rotate it over the x-axis. I think that would be the most appropriate approach by 180 degrees. I create a copy. So this should be axis, should be the axis of rotation, and the axis of rotation should go through this point. So I click OK, and now I see that there's an imperfection on this side of the flange as well, but in the different direction. That's how I would assume this flange twisting would look like over the complete width. And now I can just copy those two surfaces from the upper flange to the lower flange. And in the last step, I take all those flange plates and rotate them again, but now over the z-axis, so the vertical axis, and I carefully choose my location of the rotation axis, like so. And now I have to do this 2 times more to do this definition for the whole member length. And as you can see, with leveraging these tools in RFEM, it's quite easy and quick to create such imperfect geometries. So let's actually check how does this look now. We can clearly see that there is some flange twisting now modeled here, exactly as we want. It alternates between or from one inflection point to the other one. So this should be the most critical case in this scenario here, or the most like reasonable assumption for such flange twisting imperfection. Okay, so now last question is, how do we combine all these imperfections together? In Eurocode 3 part 1.5, we have a combination rule for equivalent geometric imperfections. We have one primary imperfection that we assign with 100%, and the other ones we take 80%. But just to make things a bit simpler here, I would just take them all with 100% amplitude, because in most of the time, or in most of the cases, there's always 1 or 2 imperfections that are not really relevant or critical for the end result. So we could either put in a lot of effort to select the most critical one and apply 100% amplitude magnitude to this, or we can just on the safe side assume the full 100% for all imperfection, and the ones that do not really harm our simulation will just more or less do nothing. Of course, we could refine it later if we want, or if we find that our solution is not economic, but due to time limitations, I don't want to do that here. So instead, I just generate an additional imperfection case with a group of imperfection, where I now superimpose the 2 imperfection cases, imperfection case 1 and 2, and I can do this very conveniently over this table, where I just define imperfection case 1 should be present together with imperfection case 2. You could change direction here very easily by modifying this factor, or also you could lower the amplitude by just putting here like 0.8 or something. If you would just want to apply 80% of the imperfection, that would also work. And then I just need to assign this group of imperfection to the load combination that I want to use for my GMNEA. For now, we only have this load combination 3 that we used, and we also need for the buckling shape imperfection. So we need to have this still defined, so I will not alter that or take this as my GMNEA load combination, but instead I want to copy it. And this one I then want to run the GMNEA analysis on. And this means I want to consider the full set of imperfections. The flange twisting is embedded or engraved into our model, and the other two imperfections are now taken into account in this load combination here. Then for a GMNEA, as we heard in the introduction, we need to take into account geometric nonlinear solutions. So we want to solve this assuming large deformations. So this means I just need to change the static analysis settings to large deformations. Of course, there are a lot of parameters you can play around with. You can change the solution method, the solver method, but in our case, we will stick with the default options since we don't have too much time to explain all the differences, but our online manual gives good guidance, and I think also in our old webinar I tackled this a bit, so feel free to refer to this. So nonlinear geometry already now included. And then I said in the beginning also that the GMNEA has the characteristic of a virtual load bearing test. That means we want to increase the load until failure. And we can do that also with the static structural stability add-on. It not only comes along with a solution for this linear stability analysis, but it also has another stability analysis type embedded, and that would be the incremental method, where I do exactly what I need. So I have an initial load factor for the start of my analysis. It would just take the design load, and then it would slowly increment the load with this factor here that I give the program. So in this case, or in the default case, that would be 10% of the initial load factor. And here you can also refine a bit the subsequent calculation steps and how it should refine the last steps and so on. But we would, the default options are quite okay for most cases, so I will stick with them. But what I would recommend, or highly recommend even, would be to save results of all intermediate load increments, because analyzing those intermediate deformation results or stress results, strain results, gives a lot of valuable information to like assess the failure mode and the behavior of the structural elements. So would always recommend to do that. And with this, 95% of the job is done. The only thing left is the nonlinear material. In the beginning, we defined a linear elastic material here without putting too much thought into that. But we, of course, need also a nonlinear material. And to assess all the nonlinear material models in RFEM, we need this additional analysis add-on here, and we also need to activate it for our model. And when we do so, we finally get access to all those nonlinear material models. And for our job, I want to use a plastic isotropic material model for steel, for surfaces and solids. And the von Mises failure hypothesis or yield hypothesis is quite fine for us. I don't want to spend too much time with the material definition. I talked about this also in our older webinar. So if you are interested to see what options the Eurocode gives us and what is suitable for such an analysis, I would highly recommend to check the old webinar. But now I will just go ahead with a bilinear stress strain model, and I want to use a hardening modulus of 1/1000 of our initial modulus of elasticity, which is valid with regards to the Eurocode rules. And because I have now taken a user-defined hardening modulus here, I also need to reset my yield strength because I made my material model a user-defined material model. Okay, and this would be all the steps necessary to set up the GMNEA analysis. The solution of this problem as we defined it would probably take like 4 or 5 minutes, and I don't want to bore you with this simulation. So I have already calculated this, or a calculated version of this. It should be more or less the same model. The only thing I think is different is that I also baked this bow imperfection into the geometry, and only the local buckling shape imperfections are defined as imperfection case. But in addition, or therefore, everything is parameterized in this model, and this is also the model I will hand over to you with the presentation and so on, so you can play around with these numbers and do your own investigation on your own geometry and your own plate girders if you like, and you can vary stuff very easily. So with this being said, let's check the deformations or the results of our load case number 4. Since we have conducted a nonlinear stability analysis, we also have results for that. And what we already see is that the highest load increment that converged was 15 with a load factor of 1.95, which is quite far away from 1. Or even if we consider the safety factors that I initially mentioned, it's quite far away from that. So that's already a good sign. And since we saved all intermediate results, we also have this slider that we can now leverage to check different results during the calculation. For example, one thing which is quite interesting is if we check the lateral deformation. I can just quickly get rid of the model and all the stuff that we don't want to see. But you can also now animate the deformation over the course of the simulation. This is also quite a nice feature. And what we see as we approach the maximum load factor is that these lateral deformation of the compressed flange excel. They really increase a lot with a small increase of load. So this would already, from looking at only on the deformation shape, give us some indication that probably lateral torsional buckling is the failure mechanism here, and is the reason that after this load step, no more additional load steps converged, so to say. We can also check the load deformation history, the global one, for example. We can display in a calculation diagram where we compare the load factor with the maximum deformation, and we can see that the stiffness of our system approaches more or less 0 at this point. And this would, negative stiffnesses are not we cannot compute with our solver. You need special solvers that are able to compute also the softening part. So this is probably the most that we can get with our methods of this analysis, and that would then also be the load factor that we would take for our failure criterion number 1. And when we remember the failure criteria for GMNEA analysis according to Eurocode 3 part 1.5, there was a second one mentioning plastic strains. So let's also address this and check plastic strains in the model. And we see that at the end, so at a load factor, at the maximum load factor, we have strains of approximately 1 per 1,000 in the flange region, in the upper flange of at midsection, so where our compressed flanges actually deform most, and also in the transition between flange and web plate. There are only very minor strains visible in the shear panels itself. So this would not be a failure criterion, so the strain-based, which would be relevant, and we would only check the 1.95 as a maximum of the load deformation curve against alpha 1 times alpha 2, which would definitely be lower than this. So that would be our check, basically. So this is quite interesting for me, at least, to get a feeling for the failure mode and to check what the deformations look like during this calculation, and what happens if we push over the linear behavior of this model, and what happens then. And it's in the next step also interesting to see what happens when we change certain parameters. For example, I simulated the same girder with the same loading conditions, just with shorter buckling panels of 3 meter. And when assessing the results here, it looked quite different. Of course, due to our imperfection, we also have some transverse deformation occurring in the model, but they are not as pronounced as before. Instead, if we now look into our strains in the model, we see that the maximum strains now are not found anywhere near midspan, but in the buckling panels close to the supports, and those are also a bit higher already, so they are not nowhere near like the 5% limit, but we can see that the strains throughout the last load increments, they increase drastically in these shear panels. So in this case, we could expect a whole different failure mode, not the global buckling, lateral torsional buckling mode, but rather a shear buckling mode in these external buckling panels here, as a critical failure criterion. Could also see how this nonlinearity or the excessive deformation in those shear panels affects the global load bearing behavior, and we can also see that the stiffness of the global system becomes much smaller. Okay, so that for me would be very interesting to see when like these different failure modes diverge, when what do I get when I change certain parameters, when I change the web thickness, for example, and so on. So that's quite a nice exercise to do, and if you have a fully parameterized model, it's very easy to do as well. Okay. So that would be all I want to say regarding the results, but maybe before we get to the summary, I would highlight that we have chosen the direction, the mode shape, and also the combination of our imperfections, in our case now for this exercise, more or less arbitrarily due to obvious time limitations. The Eurocode, however, stipulates that imperfections should combined in such a way that the lowest load magnification factor results from the simulation. This means that further investigations would be necessary, of course, so you would need to also check other imperfection directions, and especially combination of those different imperfection directions between the bow imperfection, flange twisting, and local buckling shapes. For the initial model with 4.5 meter long buckling panels, it showed that by taking a different mode shape, especially mode shape number 13, which involved this deformation in the internal buckling panels, together with a member bow imperfection, and in the second step also aligning the imperfection direction of this member bow imperfection and the local imperfections, we get a slightly smaller critical load factor of 1.82. Remember that in the initial step with our initial guess, we got a load factor of 1.95. So there's quite some difference. It would still be okay. It would still fit into the limitations, but this is of course something we cannot forget, that this is also a huge part of the analysis. Yeah. Okay, and this is more or less everything I want to highlight here. And yeah, now to the with regards to the time, I don't want to go through all the summary items I have put on this last slide. I just, as a last sentence or set of sentences, I want to highlight that a GMNEA is a very special analysis type. It requires a lot of work, a lot of thought, a lot of experience, and is of course not always or shouldn't be the first choice for design job, especially for this one. But I also want to highlight, and this is my personal opinion, that doing such type of analysis from time to time, maybe if time allows it in a certain project, you get a much better feeling of the behavior of your elements and your structure if you like also activate these non-linearities and push your model over the linear boundaries and see the failure modes and spend a bit of time analyzing the results. You get a much better feeling and engineering judgment for your future work. So I think this is still has a place somewhere in our daily routine, maybe. So, all right. With this being said, I want to hand over to Andreas again and wish you a pleasant week. Thanks for your attention. Bye bye.
Thank you, Jonas, for your nice presentation. I have an additional hint for you. You can book our online courses. For example, the RFEM 6 Masterclass course. That's a course for beginners. Then the Eurocode 2 course for the reinforced concrete design with RFEM 6. Eurocode 3 course for the steel design. And the Eurocode 5 course for the timber design with RFEM 6. Where are also course packages available. For more information, for example, for prices and content, just scan the QR codes in the middle or click on the links on the bottom of the pages. You can download the PowerPoint slides as a PDF file from our website. In the next days, you will get an email with a link to that page, and you will also find there the recording and the models. Okay, now maybe an additional information, you can get the single courses for Eurocode 2, 3, and 5, or the RFEM 6 course for free when you send us a customer project. Just write me an email and I will answer you what files I would need for such a presentation of your project on our website. And you then, when we have published it, you will get such a single course. Okay, that's also all from my side. I thank you for your attention. Thank you, Jonas, for your presentation. I wish all a nice rest of the day. Bye-bye.